So what is a sequence anyway? Essentially, a sequence is just a list of numbers. It's an ordered list of numbers because here's the first one, here's the second one, here's the third one, and so on. And there's always a pattern between all of these numbers. And since there's a pattern, we should be able to come up with a function that gives us, say, the nth term of that sequence, the nth term, the n plus 1th term, whatever. All right, now, usually we think of a function as being a continuous thing. Instead of just sticking in a 1, a 2, a 3, we can stick in any numbers in between 1 and 2. But for sequences, the domain is just the positive integers. It's an example of a discrete function. So you remember from algebra talking about the difference between a discrete function, which is just a collection of dots. And so here's our collection of dots, doop, a doop, a doop, versus a continuous one which connects all of those dots. Look at this picture right up here, of course. Continuous versus just having the dots as being discrete. All right, so in the table here, our first term is denoted with an a sub 1, and then a second one is a sub 2, and so on. Those are just the terms, the individual terms of our sequence. And then we have the nth term as denoted by a sub n. And you could see dot, dot, dot indicates that it's supposed to keep going beyond that. And then we usually represent this sequence, the whole entire thing, in a set of curly brackets. Curly brackets are set notation. That's the whole entire sequence. And then again, if you have an nth term, sequences, the implication is that they keep going. So you should also have an n plus 1th term, right? The n plus 1th term always follows the nth term, which is why we have the ellipses right after our nth term. Okay, and then this notation here looks sort of like the notation that we use whenever we're using a fundamental theorem of calculus. It just indicates that we're starting at n equals 1, and then we keep going to infinity, right? Okay, so look at the difference here. Most commonly we start at 1, as in here's the first term, here's the second term, here's the third term. But think back whenever we are doing the summations. Well, sometimes we started at 1, and then sometimes we started at 0. So we could have the 0th term and then keep going. So the notation on that one is that it starts at 0 and then continues to infinity. All right, and so that means really, doesn't this one have one more term? So it's like an infinity plus 1 sequence, which of course is still infinity. Okay, anyway, so let's take a look at an example of some different sequences. Here, this sequence is determined by this function. It's 3 plus, hey, here's our alternator right here. So instead of the alternator being multiplied by terms of the sequence, it's being added to the terms of our sequence. So here's what it would look like whenever we start plugging in. Say we plug in 1, it's going to be 3 plus negative 1, right? We plug in a 2, it's going to be 3 plus a positive 1 there, right? And then so on. So all we're doing is we're subtracting and we're adding 1 each time. So we just have a 2, a 4, a 2, a 4, a 2, a 4 over and over again. Here, let's take a look at the graph for this thing. And we call that an oscillation, right? Just like a sine graph or something like that, but we're not connecting the dots. It's just the discrete collection of those dots. Do you think that this converges to any particular number? No, it doesn't, right? It's just bouncing back and forth forever. And we're going to say that this one diverges since it does not converge to anything. All right, let's look at the next one. This time we're calling this one a b sub n. It means the same thing as a sub n. It's just the terms of our sequence determined by this function n divided by 1 minus 2 times n. So I would start with 1. We assume it didn't mark it, so we're going to start with a 1. 1 over 1 minus 2 times 1, right? So something like this, all right? And then I stick it at 2, a 2 over 1 minus 2 times 2, 1 minus 4, and so on, sticking a 3, sticking a 4, and then simplify each one of these terms. Oh, and notice that all of our terms are negative. Sometimes it's not easy to see if the terms of the sequence approach anything in particular, so we want to look at a graph. So let's look at the graph for this one, huh? All right, well, maybe it does look like this one approaches something, as if it has a limit. Well, think of this one. If you were going to take the limit of this as a function, would approach something, what do you think it would approach? L'Hopital's rule. Okay, well, let's look at this example 1c. What's the four terms of this sequence? We've got n squared over 2 to the nth minus 1. So again, assuming that we're starting with a 1, it didn't indicate it. We're going to start with a 1. We'd have 1 squared over 2 minus 1. Then we'd have 2 squared over 4 minus 1. And then a 3 squared over 8 minus 1, and so on. Here, let's simplify each one of these and maybe graph them so that we can see, do they approach anything? Well, it didn't. It looks like they had increased and then started to decrease. Do you think that this is approaching something? Well, think of this in terms of a limit. If you take the limit as n approaches infinity, what do you think that the terms of this sequence are getting close to? All right, here's another one. This one is a strangely defined function, but a famously defined function. We're going to call this one d sub n. And the first term is just 1. The second term is also 1. And the n plus 2 term, in order to figure it out, you need the nth term plus the n plus 1th term. This is a recursive series in order, or sequence, misspoke there. In order to find any particular number in the sequence, you have to know the 2 that came before it, which is why they gave us the first 2 of them. All right, so in other words, to find the third term of the sequence, it would need, this would be the second term, and this would be the first term. So it's, say it's 1, and then it's 1 plus 1, which is 2, and then a 2 plus 1, which is 3. Oh, surely you've seen the sequence before. And if we graph this thing, the Fibonacci sequence, we can see definitely it doesn't seem to be approaching anything particular other than positive infinity, right? So yeah, this one wouldn't converge to anything in particular. So again, this one is recursively defined. In order to find a number in your sequence, you have to know the ones that came before it. All right, well, yeah, I can see that this one doesn't converge, but here, let's modify this just a little bit. Shall we? Okay. And we're going to take a ratio of these terms. So you have the n plus 1th term over the nth term. Again, it's defined exactly the same way. So in other words, if we go back to our sequence, it is the 1 divided by 1. It's 2 divided by 1. It's 3 divided by 2. It's 5 divided by 3. It's 8 divided by 5. It's 13 divided by 8, and so on. It looks like this. Let's graph that one, shall we? And take a look. Does it seem to converge? Again, it seems to. Looks like it's oscillating in some kind of way, but this oscillation seems to be getting closer to something, and it's a famous number that is the golden ratio, which Donald Trump was nice enough to demonstrate with his perfect hairdo in the opening slide for this. Okay, so this one looks like it is in fact converging, which brings us to the major concern and major goal for this lesson. Not just finding the nth term to our sequence, we want to be able to determine, do the terms of the sequence get close to something? Do they converge? Or do they not get close to something? Do they diverge? So here is a divergent sequence, and then we have a convergent sequence. And we're going to examine that in terms of limits in the next video.